Welcome to part 5, folks. Let's step back just a moment here and look at the front end of the receiver right here. We'll focus on the loop antenna for just a moment, and then we'll look at the tuning condensers here as well. And then we'll move our focus down here to the oscillator section itself. Talk about some of the common failures and how to troubleshoot the oscillator simply just by looking at DC voltage. I'll put a link here in the video at the right top corner of the screen. You guys can check it out. It's where I was looking at the front end of the receiver here and trying to understand better how the loop antenna, which is nothing more than the antenna coil, resonates here across the broadcast band. Again, this being nothing but the tank circuit where you have the loop antenna, an inductor or coil of wire in parallel here with these capacitors. So that RF voltage, that's coming across through the air to the antenna itself, as it resonates, it gets stronger. And you can see here we're carrying that signal over to pin 8, the control grid of the 12SA7 for amplification. That's just one of the many things that happens in that tube. We'll come back to that in just a moment. So going back to our loop antenna right here, a couple things to look at. If the antenna coil opens, we're going to hear a lot of distortion and probably more like motorboating would be the best way to describe that. And again, at best, we would probably hear some strong local stations. So to troubleshoot the antenna coil here, or the loop antenna, we'd simply disconnect the loop from the receiver and just check for a DC resistance here between those 2 points. In my case, for this receiver, in most loop antennas, you're going to read less than 5 ohms. In my case, I read 3 ohms. And something else I took time to do as well. The coil of wire or antenna, of course, this is nothing more than an inductor. And the inductor has to be, of course, the right value to be able to resonate with the capacitance at the right frequency. So in my case, I read about 210 microhenries. So most loop antennas for your standard tuning condenser here, C1, would be somewhere just north of probably 200 to 240 microhenries. Now something else here in the loop antenna that's happened to me in the past, and probably many out there. A lot of these radios will reside in old barns, basements, sheds, who knows where. And they've taken on a lot of moisture or water. So the cardboard backing that the little loop antenna attaches to is saturated, and even the antenna wire at times is impaired by the moisture. When that occurs, the Q, the quality factor of the antenna, will be compromised. And what that leads to is reduced sensitivity. So, when you have those problems, the best thing is to try to find a substitute or rewind or create a new loop antenna. Now, if we look at the tuning condenser here, C1 and C2, C1 is the primary tuning condenser or capacitor, again made up of the rotor, which is the rotating piece, and the stator being the stationary piece. You can see here on C1, in addition to C2, the capacitance is called out. C1 again being the primary variable capacitor, and C2 being nothing more than what's referred to as the trimmer cap, which is nothing more than a compression cap. So real quickly, what happens here on C1, if you go back and look at this, and I'll pull up a picture-in-picture of a tuning condenser or capacitor, you can have shorts here between the plates, shorting the stator and rotor together, thus, compromising the receiver's ability to work. So you may find at times you'll have to clean out the dust, dirt, hair, whatever is in between those plates. In addition, the plates can be bent against each other in shorting as well, which would cause the radio to be inoperable or be compromised at part of the tuning range. Now, the little trimmer capacitors have their own unique problems as well. Most of the material that was used in between the two metal plates was mica that can become brittle, so you may find it missing or compromised. And I have replaced those with modern day plastics and still able to achieve capacitance ranges to make the tuning condenser work as designed. You'll also see physically at times the tuning condenser is isolated or insulated from the chassis using rubber grommets. So just take note of that to be sure to inspect and understand the integrity of the grommets. Some are there for isolation of signal, some voltage, and sometimes nothing more than a shock absorber for the tuning condenser itself. I had mentioned the first detector oscillator here, that 12SA7. It does a lot of stuff. There's some great theory and a tremendous resource over at Rick's channel at All American 5 Radio. So please check out his excellent presentation skills and his teaching abilities on this subject. You can learn more there about the signal amplification and how the mixing of all the carriers occurs to end up with this single IF frequency of 455 kilohertz in our case. Let's now move down here to the oscillator section that I have highlighted. As you can see here, the particular oscillator for this particular radio is one of the two-winding oscillator coils, so it's just one of the many variations that you'll see. It's very common in the All-American 5 to see this particular design. So L2 and L1, of course, here make up the oscillator coil itself. Now, the coils can open and or short, so really the best thing to do is check the DC resistance if there's problems with the oscillator. And you can see in this case the DC resistance measurements are called out. So they're easy to troubleshoot, just looking for a dead short or again a small amount of DC resistance. Now, one of the things that happens sometimes again is moisture. So depending on where this radio has been, lots of times you'll find that the oscillator coil is compromised. So maybe the beeswax that was once on the oscillator coil has deteriorated to the point where moisture has got into the coil itself. And that will make the oscillator circuit not perform as it should. So again, one thing you'll notice here, there's another tuning condenser section here, in addition to the primary tuning condenser section or capacitor that we looked at as well. So this is for the IF stage itself, and you can see again the inductance is called out, and the same issues there regarding dirt, grime, etc. can compromise this section of the tuning condenser, in addition to the trimmer C4 as well. So the same things that I mentioned earlier that apply to C1 and C2 apply to C3 and C4. So aside from the coil itself, things to be on the lookout for that are common failure points. If you look here at R1, the 22K or 22,000 ohm resistor, you can see that serves as the grid resistor, going back to pin 5 here. And if that particular resistor opens up completely or the value increases, the oscillator, of course, will fail to operate. Or you may find that the oscillator only works on part of the tuning range. So you're sitting there turning the tuning. Maybe you can get the lower portions of the broadcast band, or maybe just the opposite. You can receive the high end and not the low end, and it can tie back into a problem here in the oscillator circuit. We'll talk more about how to test that in just a moment. The one other component here in this particular design is C5. In our case, it's a 56 picofarad capacitor, or the capacity is high or low. It's going to actually compromise the tank circuit. So of course we never can discount the detector oscillator tube failing as well. It's very common to test a tube in the tube tester and it tests fine. You plug it into the radio and the oscillator will not function. So I lost count of how many times I've seen that, but never rule out a weak tube. So this 12SA7 may work well in one receiver. You throw it in another and the oscillator doesn't work, or the oscillator only allows me to tune the lower or upper part of the band. So just keep that in mind as well when you're troubleshooting the oscillator section. Don't forget to sub tubes as well, even though they test well in the tube tester. But if you suspect the oscillator's dead and not working, you really just need to check voltage at this point right here to your ground location, whether that be the common or floating ground or chassis ground, back to where R1 and C5 come together, or directly off of pin 5, the oscillator grid. Now that sounds simple enough. You're going to just check the voltage here. So what should that voltage be? Again, being it's a grid voltage, we're looking for negative voltage. If we've got 0 volts, or should we have plus voltage, we know the oscillator is not working correctly. So for the All-American 5, you're going to typically find somewhere around -5 to probably -15 volts DC across the entire tuning range of the receiver. So let's look at how to do that real quick, and what the impact of trying to measure the oscillator grid voltage is with a digital multimeter. This receiver is playing probably at maybe 20 to 50% of its potential, since we have not addressed the old capacitors that are leaky and well out of spec, I'm sure. In addition to, I would expect more resistors out of tolerance as well that we haven't addressed to this point. Now, with the radio playing, we know the oscillator itself is working. That will emulate a failed oscillator circuit here in just a moment. Do some troubleshooting. Now, one method, it's probably one of the most popular methods. You can see I've got the receiver now tuned up around maybe 1400 kilocycles or so. And I've got another receiver here tuned to 1000 kilohertz or 1 megahertz. And since the oscillator is working again, as I tune right through here, we should be able to hear the oscillator. Let me turn this up here. So you can hear that oscillator there at 1 megahertz or 1000 kilohertz, and again the dial itself would be 455 kilohertz above that. So right around 1445 kilocycles. Before we get into measuring voltages here on the oscillator tube, which is here, let me go ahead and kill the oscillator itself, and then we'll repeat this process using the little receiver here, and then we'll do some troubleshooting right in this area to see if we can understand again what the failure point is to keep this oscillator from functioning. The oscillator is not working, so let's go ahead and do some troubleshooting here. We'll go back to pin number 5, which is located right here. It's the oscillator grid, and let's look at our DC voltage at that point and see what we have. I think I had already noted we should have a negative voltage there, probably in the range of -5 to -15. Alright, let's go ahead and check voltage here. And you can see we're -0.163, but the radio is dead. Alright, let's start out here by looking at this grid bias resistor, R1. You guys can see that on the schematic. In this particular receiver, it's called out at 22,000 ohms. Let's just make certain that it's very, very close to that value. Again, I've already got the set unpowered, and I've bled off the electrolytics here as well. So I hate it when the camera dies, but anyway, I'm back, and you can see the in-circuit DC resistance is just under 21K. So that resistor is probably okay, at least it hasn't drifted high. Alright, let's look at this capacitor right here. You can see it on the schematic, C5. Should be 56 picofarads. Now, one thing odd, someone has added a resistor. Here you can see that floating. I'll do a picture-in-picture here from another shot with my camera, and added another resistor on the other side of the capacitor back to point E here on the oscillator coil. So someone may have had problems at some point trying to get this oscillator to oscillate, and added some additional resistance here, because I don't see that called out on the schematic here. So that's probably pretty close to being an in-circuit test here with the capacitor hooked up. You can see I'm just north of the 56 picofarads. So I'm not overly concerned at this point in time with that reading. Alright, let's look at L1 here, and I'll pull up the schematic if I can get down in here. This will be points A to C, and you can see we're looking for about 1.2 ohms. And again, I may be influenced because I'm doing this in circuit at 0.7 ohms. So I'm not really worried about that reading at this point in time. Let's go back to L2 and read across that coil, and just make sure it's not compromised. And again, we're looking for connection points between E and B, and we should read around 5 ohms or so. And here you can see we only have 0.1, 0.2 ohms, so something is going on here on the L2 coil, and that's got our oscillator disabled. So what I did, guys, to simulate a failure, you can look here in the picture-in-picture on the schematic, I shorted out the tuning condenser here for the local oscillator. And if I remove the short from the stator to the rotor, you can see our resistance comes back up to 5 ohms, which is a good match here, looking at the schematic. That's one of the things I mentioned that could happen. So if the tuning condenser itself is shorted and or open, of course, the oscillator would not function. So with the short removed, let me get these leads off. Let's power the radio back up, and let's look at the DC voltage again on the oscillator grid, pin number 5, and see what we read. So you can see the radio is playing again. That's a good sign, so we know we've got that oscillator issue resolved there by removing the short off of the oscillator tuning capacitor. Let's probe around now and read voltages here. Alright, you can see there about 5.59 volts. Let me just spin this thing around the dial. Alright, so we've got negative voltage here at that point across the entire span here of the tuning condenser. Let me turn this back up just for a moment. Remember that station we could pick up here just a moment ago, just around 1400 kilocycles? You can't hear that now, and the reason why, even though I'm using my digital multimeter here, the Fluke, which has a internal impedance of around 10 meg, we're still loading the circuit. Take that off here and see if we can you can hear I can bring that station back. So the loading here is a problem. So there's a workaround solution when you're working in a grid circuit. And let me demonstrate that just for a moment here. So let's look here at how the circuit itself is loaded by the multimeter and the associated test leads. We'll start out here. Let's read the capacitance of the meter here and just see what we show. Okay, you guys can see I'm just hooking up my meter leads here. Got the meter turned on, looking at DC voltage. And now let's turn on the little LCR meter here. And you can see we're reading about 57, you might as well round that up here, to 58 picofarads of capacitance. So the workaround to lower that capacitance, Mr. John Ryder came up with the solution and coined that back when they created the DC probes for the VT/VM meters. And by using a 1 meg resistor here, we can reduce the capacitance back down to probably a couple picofarads. So let me hook up the 1 meg ohm resistor here. Alright, you can see the 1 meg ohm resistor here. Let's flip on the meter now. And you guys can see the impact that that had to the capacitance here. So let's hook that back up to the circuit and measure the DC voltage now and see what difference that makes. So here we go. You can see I'm tuned to a local station here. Let me hook back up here to the oscillator grid. And you can hear what's happening there, and you can see the DC voltage readings. So we've mitigated the loading being created by the meter itself and the leads just by adding the 1 meg ohm resistor. So a little trick you can use. Now the DC voltage readings that we're reading are going to be about 90% of the value in this configuration, with my meter being about 10 meg ohms and the 1 meg ohm resistor. But we can fix that. What you would do, and I'll show the math here in the screen, if that's important to have a precise number, is take the DC reading, well, let's just call it 7.90 in the example math. We'll divide that number by 9 and then multiply that number by 10 to get the approximate DC voltage on the oscillator grid. So again, you can see, using another receiver here, I'm tuned to 1000 kilohertz or 1000 kilocycles, 1 megahertz, however you want to call it. And you can see the radio itself would be tuned 455 kilohertz below that, and you can hear the oscillator working. Now again, you could use a scope as well. You have one, and let me demonstrate that as well. So you can see I've got a dip meter, and I'm going to just leverage the coil itself, which is designed here to cover 0.7 to 1.6 megahertz. You could use a coil of wire. I'm just using this because it really should help resonate here across the band, and I can put it here in close proximity to the oscillator coil itself, and you guys can see the oscillator here. Or I can put it near the oscillator tuning condenser. And you can see I can pick up the oscillator there as well. So let me just rotate this. And the reason you're seeing the peak would just be this particular coil is resonating there at that center frequency. So just shows you another method and procedure you can use as well for validating the oscillator is actually working. So I appreciate you guys watching this video. Hopefully you found it helpful. The oscillator circuits used to be very intimidating to me. And again, many times you're going to find it's just a bad tube anyway, or a tube that's just not happy working in the circuit for some particular reason. But if not, on these simple All-American 5s, I hope these few troubleshooting points here would be something that would be helpful if you do encounter an oscillator that's not functioning. So you guys take care, stay well, and hopefully I'll have another video published soon. We'll take off from this point and catch the remaining part of the circuit that we haven't touched on, from the IF section back over to the audio detector. And then I'll spend some time offline recapping and checking all of the resistors, and then I'll bring you guys back. We'll do an alignment and see how well the radio receiver plays with the modern day components in place. Thanks again for watching and subscribing to my channel.